proceeding further, just a quick review. You have come across E2 eliminations. So E2 eliminations can be following syn elimination or anti-elimination, because it is a E2 elimination by molecular, in which the concentration of base and the concentration of the substrate both makes a difference. But in case of syn elimination, you have come across there is no base. So base is not required. But both groups leaves eclipsing each other. So that is in fact syn elimination. But in anti-elimination, both base and substrate, these are involved in the elimination process. So this is the example you have come across, that any functional group, good living group that you have seen in case of aliphatic substitution reaction, aliphatic nucleophilic substitution reaction, SN reaction we commonly call. In such a case, you have come across that substitution reactions have a good living group. So although whatsoever this is tosylate, this is brosylate, nosylate, all right, triflate, nonoflate, etc. So whatsoever is the good living group, even including the diazonium, or it may be a ester group, it may be a halide, etc. So whatsoever good living groups, so these always leaves anti-fashion, mean good living group, and the hydrogen from the next hydrogen carbon undergoes elimination at 180 degree. So this is, if you look at the functional group and the reaction condition, then you can decide what it is going on. So one parameter you have come across, elimination is favored at high temperature. Similarly, you shall see elimination is also favored when we are using a good base. So I shall introduce a good base a few slides later. So even elimination is just like you have compared SN2 versus SN1. SN1 takes place when you have a tertiary substrate. SN2 happens when you have a primary substrate. When you have a secondary substrate, secondary carbon is undergoing elimination or substitution, then it always undergo SN1, SN2 mix. You have come across that already. Is everybody listening me?
Yes sir. सर
All right.
आपकी स्क्रीन नहीं शो हो रही.
This is the problem. That's why I asked. I don't know why this happened. Let me try again. Now is it clear?
Yes sir. Yes.
So even elimination and E2 elimination are very similar to SN2 and SN1 if the leaving group is attached to a tertiary carbon, just like here I have presented in previous lecture. If R3 and R4 they are alkyl or aryl groups, then definitely this carbon shall be a tertiary carbon. If it is a tertiary carbon, it shall follow E1 mechanism. If let's say R3 and R4 both are hydrogens, then it shall follow E2 elimination. But if one of them is alkyl, other is hydrogen, then it depends upon the nature of the alkyl group that we shall see in next slide. So anyhow, E1 elimination, just like SN1, it follows two steps. First step is slow, second is fast. In first step, it is very similar to the SN1 mechanism. A good living group leaves, generates carbocation. This is very similar. And if we have a weak base, then it shall compete, substitution shall compete with elimination. If we have a good base, then substitution shall not be favored, rather elimination. So it all depends to the quality of the base, which base we are using. So in this case, when tertiary carbocation is generated, the base picks up a proton from next carbon, and this hydrogen leaves without electron pair, generating a double bond. Now there is a carbon-carbon free rotation. So when it is leaving, these two groups can rotate. So we can have R3 this side, R4 that side. So we shall have both isomers possible, just similar to SN1 mechanism. So I have yesterday presented this one example to include this. Now we shall switch over to the substrate nature. The E1 elimination and E2 elimination also depend upon the substrate's nature. If our carbon where leaving group is attached, which leaves with the electron pair, if this is a tertiary carbon, definitely it shall undergo E1 mechanism, no E2 at all. And similarly, if the carbon is secondary, it may undergo E1 or E2 or maybe mixed. So, but if it is just similar to substrate 2, secondary carbon, in 3, this is also secondary carbon, in 4, this is also secondary carbon. So, in all these substrates 2, 3, and 4, the carbon where leaving group is attached is a secondary carbon, but next to this carbon, we have a olefinic double bond or alkyne triple bond, or we have a aromatic system attached, or we have an electron donating group by resonance. If any three of these are attached here, then this molecule or this follows a E1 elimination. So mechanism you have come across yesterday, this actually generated this positive charge which is resonance stabilized. This resonance form is more stable, this is less stable, that's why hydrogen leaves from this carbon, generating a double bond here. Similarly, X leaves generate a positive charge here. This positive charge is more stable, and you can see this is resonance stabilized. So a hydrogen from here base picks up and releases a double bond at this position, generating this entity. Very similar if this Y is an electron donating by resonance, so it generates a positive charge, it stabilizes this charge, and we get a double bond at this position. So this is if to a olefin we get a pi, it may be a double bond or a triple bond, olefinic double bond or alkynic double bond. It may be aromatic system, it may be a carbocycle, it may be a heterocycle. So if we have an electron donating by resonance, mean it is plus R group. So in that case, these systems 100% favors even elimination, although the carbon where leaving group is attached is a secondary carbon. All right. So all such substrates follow even elimination protocol. So just a very quick review that which basis favors elimination. Now there are so many bases being used right from very beginning, but I am just introducing three of them here. Normally, pyridine and triethylamine were used as the base. Triethylamine is a tertiary amine, and pyridine is a lone pair of nitrogen is not involved in resonance in case of pyridine. Let's say this is a structure of pyridine. If you don't have this group attached here, if you don't have dimethylamino at this position, then this is simply pyridine. Pyridine is a common name. Actual IUPAC name is azine. So this is the pyridine. You can see this nitrogen, this lone pair is along the plane of this aromatic system. You would have come across already in resonance. This lone pair of nitrogen, this has a pi orbital parallel to this, but the pi orbital present on every carbon, including this nitrogen, is perpendicular to this plane. So this pi orbital here, this pi orbital here, and our orbital here, that of nitrogen, non-bonding electron pair. So they are not in a plane, they are perpendicular to each other, 90 degrees to each. So this nitrogen lone pair is not delocalized. This is located on nitrogen. It is 100% localized. As a result, pyridine and triethylamine are almost have same pKa value or very close pKa value. They are equal good bases. But triethylamine, a second, if we have a tertiary amine just like this, whenever it donate electron pair, whenever it donate electron pair, this nitrogen becomes positively charged. So if it becomes a positively charged, it cannot carry out substitution. Let's say if this entity is generated, if we have a pyridine, nitrogen make a bond as a substitution product, just like we have come across here. We have generated this one or this one. So if our base, let's say pyridine we are using as a base, so it is acting on this hydrogen to leave. But if let's say it is trying to act as a nucleophile, then it shall approach this orbital from above or below, and it shall generate a positive charge on nitrogen, because nitrogen is making four bonds. If that is the case, then positive charge on nitrogen is not tolerable, it shall reverse back. This is the reason why we are using tertiary amines as a good basis. So as a result, rather we use pyridine, another derivative is used for this, which is called, it is at 4 position, mean nitrogen from heterocyclic atom, the numbering is always taken place. Nitrogen is number 1, this is 2, 3, 4. At 4 position, we have a functional group, which is amino, but this amino is substituted by 2-methyl group. So it is a dimethyl amino functional group. So dimethyl amino. So I have written dimethyl amino pyridine. Otherwise, you can write dimethyl 4-dimethyl aminoazine. But because it is been abbreviated as 4-DMAP, this is the abbreviation we use for this system. This is called 4-DMAP. That's why I retain pyridine here. Pyridine is a common name for this heterocyclic system, but actual IUPAC name is azine. So this 4-DMAP is a very good base. Now just look at here. This is a nitrogen, which is a tertiary aminic. This nitrogen is attached with 2-methyl and 1-phenyl. So this nitrogen is tertiary aminic. This nitrogen is also tertiary. But look at here. This nitrogen is sp hybridized. This nitrogen is sp3 hybridized. This is a difference. Now, either this nitrogen act as a